So we've talked about how moment of inertia is the rotational equivalent of mass. The next question is, what is the rotational equivalent of a force? Because we're working towards trying to build up an F equals ma type understanding of rotational motion. So how do we figure out what kind of force causes something to start engaging in rotational motion? Well, let's first break it down in kind of common sense here. Let's say we have this pen, and let's say we fix an axis of rotation over here, so the pen can rotate like this. And let's just look at what kind of a force do you need to get this pen to rotate, and what are the important properties of that force. So observation number one, if I exert a force like this, it does not cause the pen to rotate. So not any old force will cause the pen to rotate. Even if I push in this direction really hard, all it will do is move the pen laterally. It can't possibly cause a rotation in this direction. On the other hand, if I rotate that force perpendicular and I exert a force like that, it causes a rotation really easily. Or if I exert a force like that, it causes a rotation really easily. So what's the difference between a force that goes like this and a force that goes like this from the standpoint of rotation? Well, let me explain. When it comes to these forces in rotational motion, it's not only the magnitude of the force that matters, but also the direction of the force and also where the axis of rotation is located. So first off, the rotational equivalent of a force is called torque. Okay, torque is the rotational equivalent of force. It causes I should say, changes in rotational motion, just as forces cause changes in translational motion. So the amount of torque that's exerted depends on a number of different things, just like moment of inertia depends on a number of different things. It depends on the magnitude of the force, obviously. It depends on the direction of the force. So the vector nature of the force is going to be important. It also depends where the force acts on the object, which is going to translate in everyday language into the amount of leverage that you have with the force, basically. In my example here, I didn't show that, but if I exert a force here, that's going to have a different effect from if I exert the force here. See, I don't get as much of a rotation from what's probably about the same amount of force. And if I exert the force here, it can't cause any rotation, even though it's the same magnitude and direction force as what I had before. The other thing that matters is where is the axis of rotation. So as I mentioned in previous video, where the axis of rotation is located is going to be really important for all of these rotational properties. Now, let me be a little bit more specific. How do you calculate? Suppose you know the force. How do you calculate the torque from the force? There's actually a couple different ways to do it. Let me show you my favorite method in this video, and I'll show you the other popular method in a different video. The method I like to use, I refer to it as the force component method, because it really relies on the vector nature of the force and your ability to break forces into their components. But to me, it makes the most sense. Like, I can understand very clearly why this method works, which helps me to remember it and helps me to get it right. So in the force component method, you come back to this point I was making before, that a force in this direction doesn't cause any rotation, and a force in this direction does cause a rotation. So think of those two directions as being the two components of any force vector. So in the force component-based method, you are going to break your force vector into two components, one pointing toward or away from the axis of rotation, and the second one points perpendicular to the axis of rotation. So in other words, in my example, this component would be towards the axis of rotation because the axis of rotation is here. So it makes a straight line directly to the axis of rotation if I exert a force like this. If I exert a force like this, it's perpendicular to the, if you drew a line connecting the axis of rotation to where the force is acting, the force is perpendicular to that line. I should probably be more clear than saying perpendicular to the axis of rotation. It's really perpendicular to the line connecting the axis of rotation to where the force acts on the object. So if you can identify these two force components, then the rest of it is easy. The formula is that the torque, this is the symbol we normally use for torque, that's a lowercase Greek letter tau, which looks kind of like a lowercase t, is equal to only the, I call it the tangential component of the force for reasons that I'll explain. So this is this second component of the force. That's what this refers to. Times, I call it L, and L is the distance from the axis of rotation to the point where the force acts on the object. So in other words, you need to see where the force is acting on the object, see where the axis of rotation is located. So in this case here, the axis of rotation is here. The force is acting over here. So L is the distance here between the axis of rotation on one end and the point where the force acts on the other end. And then you take the force component that's perpendicular to that line. I call it tangential because if you picture a circle here, if you picture the pen can rotate in a circle like this, if you visualize that circle, so that circle is going like this in the video, the force component that I'm interested in would be tangent that circle. If you picture the circle going like this and a tangent line like this, those are the things you really need to know. So let me do a separate video just breaking down the procedure for converting a force into a torque in a more step-by-step way. This is kind of like the general overview. I should also mention here, this is basically how you would calculate the magnitude of the torque. The direction of the torque, we're not going to worry in this class really about the whole vector nature of the torque. For our purposes, there's really only two possible directions of the torque. It could cause the object to rotate clockwise or counterclockwise. So if you picture the axis of rotation, it could rotate this way or it could rotate this way. So we'll call these positive and negative torques. One that causes it to rotate counterclockwise would be positive, and one that causes it to rotate clockwise would be negative. So a torque that causes counterclockwise rotation is plus, and a torque that causes clockwise rotation is minus. So that's how you sign the torque. That's at least the easy way to sign the torque.